In this video, we're going to talk about some common concepts that are typically taught in the second semester of physics. So let's go over charges. Now you know that like charges, such as two positive charges, will repel each other. They will feel a force that will push them away from each other. Whereas opposite charges, they attract each other. So if you have a positive charge and a negative charge, these two will feel a force of attraction. And you could quantify this force using Coulomb's law. And here it is. So the electrostatic force between two charges is equal to K times Q1 times Q2 divided by R squared. Now K is a constant. It's equal to 9 times 10 to the 9, and the units are newtons times square meters per Coulomb square. So that's just a fixed value. Now Q represents the electric charge, and Q is measured in coulombs. R is the distance between the charges. And now let's think about what this equation tells us. If we were to increase the magnitude of, let's call this Q1 and Q2. So let's say Q2 increased from 100 microcoulombs to 200 microcoulombs. What do you think the magnitude of the force will be between the two charges? If you increase the magnitude of the charge, the electrostatic force between the charges will increase. In fact, if you double Q2, then F will double in value. If you double Q1, F will double in value as well. If you double both Q1 and Q2, F will increase by a factor of 4 because 2 times 2 is 4. Now, what happens if you increase the distance between the two charges? So let's say here's charge 1 and here is charge 2. And let's say the force that's acting on each charge is 100 newtons when the distance between them is 1 meter. What's going to happen if we double the distance between the two charges while the magnitude of the charge is still the same? So now the separation distance is 2 meters. Will the electrostatic force acting on the charges, will it increase or decrease? Well, because the charges are further away from each other, we expect that the force that's acting on them will be weaker. And so anytime you increase the separation distance, the electrostatic force acting on these charges will decrease. You can liken this to a relationship. When you're close to each other, the bond is stronger. But when you're further away, the bond is weaker. And the same is true for charges. Whenever you have two electric charges that are very close in distance to each other, the forces acting on those charges will be strong. Whereas if they're far apart from each other, the forces acting on them will be weak. Now, if we double the distance, what's going to happen to the magnitude of the force? So using Coulomb's law, here's what you can do. For these types of questions, for any variable that doesn't change or any constant that doesn't change, replace it with a 1, except for the one that changes. So K, Q1, and Q2 are not changing in this case, so I'm going to replace it with a 1. Now the distance increased by a factor of 2, and so I'm going to replace R with 2. But because R is squared, I need to square the 2, and 2 squared is 4. So the force is going to be 1/4 of what it was before. 1/4 of 100 is 25. So now the force acting on each charge is 25 newtons. Now let's say we have a positive charge and a negative charge separated from each other by a distance of 3 meters. We'll call this Q1 and Q2. Now let's say the force acting on each charge is 500 newtons. So what's going to happen between the forces acting on those charges if we bring the charges closer to each other? So let's say the separation distance is now 1 meter instead of 3 meters. So we reduce the distance by a factor of 3. And at the same time, let's double the magnitude of charge 1 and let's triple the magnitude on charge 2. So by what factor will the force increase by? So using Coulomb's law, F is equal to K Q1 Q2 over R squared. The best way to get the answer is to replace everything with the amount that we changed it by. Now K is the same, so let's replace that with a 1. Charge 1, we doubled it. It went from 1 Q1 to 2 Q1. So we doubled Q1. We tripled Q2. And R was reduced by a factor of 3. So it's 1/3 of its original value, and we need to square it. So 2 times 3 is 6. 1 over 3 squared. 1 squared is 1. 3 squared is 9. So this is 6 divided by 1 over 9. Let's multiply the top and the bottom by 9. 6 times 9 is 54. 1 over 9 times 9 is 1. The 9's cancel. So the force will increase by a factor of 54. Now the original force was 500. So the new force acting on these two charges is going to be 500 times 54, which is 27,000 newtons. So to review, make sure you understand this between charges. If you increase the magnitude of the charge, the electrostatic force acting on them will increase. If you decrease the distance, the electrostatic force will increase. Now let's work on a simple math problem relating to Coulomb's law. So let's say that Q1 has a magnitude of 200 microcoulombs and Q2 has a magnitude of 300 microcoulombs. Now let's say the separation distance between the two charges is 80 centimeters. Calculate the magnitude of the force between them. So we could use this equation. F is equal to K Q1 Q2 over R squared. Feel free to pause the video and try this. So K is 9 times 10 to the 9. Q1 is in microcoulombs. Micro is 10 to the negative 6. So 200 microcoulombs is going to be 200 times 10 to the minus 6 coulombs. Now for Q2, we don't have to worry about the negative sign because if you're looking for the magnitude of the force, it's always going to be a positive number. The only thing we need to worry about is the direction. The direction of the force acting on Q1 is going to be towards the negative charge, and the direction of the force acting on Q2 is going to be towards the positive charge. So when dealing with opposite charges, you're going to have a force of attraction. When dealing with like charges, like 2 positive charges or 2 negative charges, you're going to deal with a force of repulsion. So Q2, we're going to replace it with 300 times 10 to the minus 6 coulombs. Now the distance between the two charges is 80 centimeters. 1 centimeter is 10 to the minus 2 meters. And so you can write 80 times 10 to the minus 2 meters, and then we need to square it. So let's go ahead and plug in this whole thing. So you should get 843.75 newtons as the electrostatic force acting on these two charges. That's the answer. Now you might be wondering what is meant by electric charge. You heard of that term before and you have an idea of what it is, but what really is electric charge? Q, the symbol for electric charge, represents the quantity of charge. When Q is negative, what this means is that you have more electrons than protons. And when Q is positive, there are more protons than electrons. The charge of one electron is equal to negative 1.6 times 10 to the negative 19 coulombs. The charge of one proton is positive 1.6 times 10 to the negative 19 coulombs. So let's say if we have a charge of positive 100 microcoulombs. What does that mean in terms of protons and electrons? So using this conversion factor, one proton has a charge of positive 1.6 times 10 to the negative 19 coulombs. We can determine the number of excess protons that represent this charge. So let's say if we have a piece of metal with a charge of positive 100 microcoulombs, there's more protons than electrons in this object. Now to quantify it, we're going to convert coulombs to protons. 100 microcoulombs is 100 times 10 to the negative 6 coulombs. And we know that one proton has a charge of 1.6 times 10 to the negative 19 coulombs. Make sure you set it up in such a way that the unit coulombs will cancel. So now let's divide 100 times 10 to the minus 6 by 1.6 times 10 to the negative 19. And so the answer is positive 6.25 times 10 to the 14 protons. So what this means is that there's this many protons more than electrons. This doesn't tell you how many protons are in the object or in the metal. It simply tells you how many protons or how many excess protons that you have relative to the number of electrons. Because in the metal, you're going to have both electrons and protons. So let's say if there were 1.5 times 10 to the 14 electrons, and the object still have a net charge of positive 100 microcoulombs. How many protons will there be? So this number is the difference between the number of protons and electrons. It just means we have that many more protons than electrons. All we need to do to get the answer is we need to add these two numbers because there's going to be more protons than electrons. So 1 plus 6 is 7, and 0.5 plus 0.25 is 0.75. So we're going to have 7.75 times 10 to the 14 protons. And so that's how many protons would actually be present in that object, given this charge. So that's how you could find the answer. Now let's say if you have an object with 4.8 times 10 to the 16 electrons, and it has, let's say, 2.5 times 10 to the 16 protons. So what is the net charge in this object? What would you do to find the answer? Now there's a simple formula that can help you to calculate the answer. The net electric charge, you could use lowercase q, or sometimes capital Q will be used for that. So the net electric charge is going to be the difference between the number of protons and electrons times the individual charge of a proton or an electron. That is the absolute value of that charge. And so that's all you got to do. So in this case, we have 2.5 times 10 to the 16 protons, and we have 4.8 times 10 to the 16 electrons. Let's multiply by this number. So 2.5 minus 4.8, that's a negative 2.3. And it makes sense why it should be negative, because we have more electrons than protons, and so Q has to be equal to a negative number. Now, if we multiply these two numbers, this will give us negative 3.68 times 10 to the minus 3 coulombs. Now, 10 to the minus 3 is associated with the prefix milli. So we could say that this is negative 3.68 millicoulombs. And so we can write the final answer like this. So as you can see, if you have more electrons than protons, the net charge will be negative. Now let's go back to electric forces, because sometimes you'll be given a situation where you have multiple charges, like this one. Now let's focus on the concept more than the math associated with these types of problems. Let's call this Q1, Q2, and Q3. And here is the question. What is the direction of the net electric force acting on Q2? Is it this way? Is it that way? Is it going north? Is it going south, east? What is the direction of the net electric force? And let's say that each charge has the same magnitude and all of the charges are equidistant from each other. So let's say Q1 and Q2, they're 1 meter apart, and Q2 and Q3 are also 1 meter apart. Now, focusing on Q2, Q2 is attracted to Q1, and so it feels a force that pulls it to the left. Q2 is also attracted to Q3. It feels a force that pushes it down. And so if you combine these two vectors, if you go to the west and also south, the resultant force vector will be directed southwest. And so at this instant of time, Q2 is going to feel a force that's going to pull it in this general direction. The video that you're currently watching is the first half of the entire video. For those of you who want access to the second part of the video, I'm going to put it on my Patreon page, which you can see the link on the screen. And if you wish to support that page, you can gain access to the second part of the video. Now, in that video, I'm going to talk about capacitors, how they work, and some things you need to know about them. In addition to that, circuits, Ohm's law, Kirchhoff's voltage law, his current law, and also series and parallel resistors and things like that. So feel free to take a look at that video if you want to. And I do have some other video content that you might be interested in on my Patreon page. So when you get a chance, feel free to review it. And now let's get back to this video. Now let's try another problem. So let's say that this time we have 3 positive charges. We'll call it Q1, Q2, and Q3. What is the direction of the net electric force acting on Q1? Let's say, just like before, the charges have the same magnitude and they're equally spaced apart. What is the direction of the force acting on Q1, or approximate the direction? Now, Q1 is repelled by Q2. So Q2 causes Q1 to move in this direction. Let's say the distance here is 1 meter, and the distance here is 1 meter. Now the distance between Q1 and Q3 will be more or greater than 1 meter based on the Pythagorean theorem. So if you basically use C squared equals A squared plus B squared, if you take the square root of 1 squared plus 1 squared, you're going to get the square root of 2, which is about 1.4. And so because the distance between Q1 and Q3 is greater than that between Q1 and Q2, the force that is exerted on Q1 by Q3 is going to be weaker than this force. But this force will be in this direction, but we should draw a smaller vector. So I'm just going to make that vector smaller. Now, if we were to combine these two vectors, what would we get? One way to add vectors graphically is to draw them from head to tail. So if we draw the first vector, which is going to be longer, let's call this F2 because it was based on charge 2. We'll call this F3. And then the second vector, which is going in this general direction, but it's shorter. And then starting from the original position to the final position, this would be the resultant vector. We'll call it FR. So it looks something like this. So that's going to be approximately the direction of the resultant electric force acting on Q1. And so that is our answer. Now let's talk about something known as the electric field. This is the next topic beyond electric force. So what is the electric field? The electric field is defined as the force exerted on a positive test charge divided by the magnitude of that test charge. And so here's the formula for the electric field. It's equal to force divided by charge. So let's say if we have a positive charge, and let's say this positive charge has a magnitude of 50 microcoulombs, and it feels a force that pushes it towards the right. And let's say the magnitude of that force is 0.02 newtons. What is the electric field at that point in space? So using this formula, it's simply the force exerted on the charge divided by the magnitude of that charge. So it's 0.02 newtons divided by 50 times 10 to the minus 6 coulombs. So the electric field in this region of space, which the positive charge currently occupies, the electric field in that region is 400 newtons per coulomb. And so the electric field is basically the ratio between the force exerted on a charge divided by the magnitude of that charge. So think about what this number means. So this electric field tells us that at that point, it can exert a force of 400 newtons per every coulomb of charge. So if you have a charge of 1 coulomb, so let's say this is a positive charge of 1 coulomb, it will exert a force of 400 newtons. Now, if we double the magnitude of the charge, but the electric field is still the same, that is 400 newtons per coulomb, the force exerted on that charge will be 800. And so, as the magnitude of the charge increases, the force that's exerted on that charge by the electric field will increase. And so the electric field gives you a ratio between how much force will be exerted per unit of charge. So if we have, let's say, another positive charge with a charge of 5 coulombs, the force exerted on it will be 5 times 400, and so it's going to be 2,000 newtons. So let's say that we have an electric field vector that is directed east. What's going to happen if we place a positive charge in this electric field? And let's compare it if we place a negative charge in that same electric field. So what you need to know is that a positive charge will feel a force in the same direction as the electric field. A negative charge will feel a force that will accelerate it in the opposite direction of an electric field. So let's say if we have an electric field directed north. So go ahead and draw the direction of the electric force acting on these two charges. So the electric force acting on the positive charge will be directed north in the same direction as the electric field. For the negative charge, the electric force will be directed south, opposite to the direction of the electric field. Now, it's important to understand that every charge can create its own electric field. The electric field created by a positive charge emanates in all directions away from the positive charge. Now, the electric field created by a negative charge always points towards the negative charge. Now, why is this important to know? Sometimes you might be given a situation where you have multiple charges. Let's start with a simple situation. Let's say we have a positive charge and a negative charge. And we wish to determine the direction of the electric field at 3 points. Let's say at point A, at point B, which is at the midpoint between Q1 and Q2, and also at point C. What is the direction of the electric field at these points? Well, let's start with point B. So to determine the electric field exerted by Q1 at point B, draw a line from Q1 to point B. We'll call this E1 because it was created by Q1. Now, to draw the electric field vector created by Q2 at point B, remember, from a negative charge, the electric field created by it has to go towards the negative charge. So E2 will be a vector starting from point B, drawn to the negative charge. So it will be in this direction. So at point B, the net electric field will be directed east because it's the sum of these two vectors. Now let's focus on point A. The electric field at point A created by Q1 will be in this direction. So this is going to be E1. So you need to draw it from the positive charge to the point. So remember, the electric field created by any positive charge always emanates away from the positive charge. Now the electric field created by Q2 at point A, because it's a negative charge, we need to draw it from the point pointing towards the negative charge. Now this vector is going to be smaller than E1. And the reason why E2 is smaller than E1 is because Q2 is further away from point A than Q1 is. Because Q1 is closer, the electric field created by Q1 is going to be stronger than Q2. So here's the formula for the electric field created by a charge. It's KQ over R squared. As you increase the magnitude of the charge, the electric field increases. As you increase the distance, the electric field decreases. And that's why E2 is less than E1 at point A, is because the distance between Q2 and A is greater than the distance between Q1 and A. And so that's why E1 is stronger, but E2 is weaker. So the net electric field at point A is going to be directed west as opposed to east because E1 is greater than E2. Now at point C, to draw E1 is going to emanate away from the positive charge towards point C. So it's going to be going in this direction. And for E2, it's going to point towards the towards Q2, that is towards the negative charge. And it's going to be bigger because point C is closer to Q2 than it is to Q1. So this time, E2 is greater than E1. And so the net electric field will be directed west again because this vector is bigger than this one. And so that's how you could determine the net electric field at a certain point if you have multiple charges. Now, let's say if we have a positive charge in this region and a negative charge here. And so let's call this Q1 and Q2. What is the direction of the net electric field acting at point A? So feel free to pause the video, draw the vectors, and determine the net electric field vector at point A. So Q1 is going to exert an electric field in this direction towards point A. Q2 is going to exert an electric field toward itself from point A in this direction. So if we add those two vectors, the resultant vector, so we have E1 going in this direction and then E2, so the resultant vector is here. So this is where we started and this is where we finished. So at point A, the net electric field is going in this direction. So it's going in a northeast direction. Let's try another problem. So let's say we have 3 charges. Let's say Q1, Q2, and Q3. And let's say that they're equally spaced apart. So let's say the distance between Q1 and Q2 is 1 meter, and the same is true between Q2 and Q3. What is the net electric field at point A? What is the direction of the net electric field at that point? So Q1 is going to exert an electric field away from itself towards point A, and the same is true for Q2. Positive charges always direct an electric field away from them, and the electric field will always point toward the negative charge. And so these are the 3 vectors that we have. And all the charges have the same magnitude, and so E1 and E3, they're going to be the same length. However, E2 should actually be the biggest. In terms of distances, let's say that the distance between Q2 and A is 1 meter. This is going to be about 1.4 meters, and this is going to be 1.4 meters. So the electric field vectors for those two should be the same. But this one, because the distance is the shortest, it's going to have the greatest electric field. So E2 is greater than E1 in terms of magnitude, and E1 and E3, they have the same magnitude. So that's going to give us, let me just delete this first. That's going to give us a good idea of how long we should draw the relative vectors. So we said E2 is greater than E1, and E1 is equal to E3. So we're going to say that E2 is about that long. E1 is going to have to be shorter, and E3 will also be shorter, but the same length as E1. So how can we add these 3 vectors so that we can get a general idea of the direction of the net electric field at point A? Now, what we need to do is break up E1 and E3 into its components. So E1 has a y component that is going in the negative y direction, and E2 has an x component that's going in the positive x direction. E3 has a y component going up and an x component going in that direction. Actually, I need to correct this. E3 should be going towards the negative charge. So correction. I had it before, but for some reason I had it pointing towards A. But the electric field created by a negative charge should always point towards a negative charge. So E1 still has a y component going in a negative y direction and a positive x component. Now E3 has a negative x component and a negative y component. Now, because E1 and E3 are of the same magnitude, we could say that the x component of E1 and the y component, the x component of E3, they cancel because they're anti-parallel and they're the same length. So we could cancel those two. Now, notice that the y components, they're parallel. They're going in the same direction. And so we can add those two y components to form a bigger vector going in the y direction, which I'm going to draw in blue. And now let's combine that with E2, which is going in this direction. And so the net electric field, if we combine these two vectors, or let's delete this one and just add it here, we can see that the net electric field is going to be in that direction. And so that's how you could determine the net electric field vector for this particular problem. Let's say if we have two charged metal plates. On the left side, this plate will be positively charged, and on the right side, this will be negatively charged. Now, what's going to happen if we place a positive charge near the positive plate? What's going to happen? Now, there is an electric field in between the two plates. We know the electric field emanates away from the positive plate and points towards the negative plate. If you recall, positive charges create an electric field that emanate away from them, and negative charges create an electric field that points towards them. So the net electric field in between these two plates is directed towards the negative plate. Now, the positive charge will feel a force that will accelerate it in the direction of the electric field. Now, this electric field, would you say it's doing positive work or negative work on the charge? Let's say the charge was initially at rest at point A, and it's moving to point B. In this case, the work done is positive. If you recall, work is equal to force times displacement. Because the charge is moving to the right, its displacement vector is towards the right. If the force and displacement vector are parallel, then the work done is positive. Because the work done is positive, the kinetic energy of the object is increasing. And also the fact that the object is speeding up. It's moving from rest and it's accelerating towards the right. So anytime the speed of an object increases, the kinetic energy increases. And if the kinetic energy increases, that means that the potential energy must be decreasing. Now, let's say if the positive charge is placed towards the middle or somewhere near the middle of the two plates. And let's say initially this charge is moving towards the left. Now, what can you say about the work done by the electric field on this charge? At this instant of time, as it moves initially to the left, the electric field still exerts a force that is parallel to itself. So the electric force acting on this charge is still directed towards the right. And it makes sense because the charge, the positive charge, is repelled by the positively charged plate, but it's attracted to the negatively charged plate. And so even though it's moving to the left, due to its initial momentum, it feels an electric force that is pulling it towards the right, towards the negatively charged plate, because opposite charges attract each other. And so right now, the charge has a displacement vector to the left, but the force is towards the right. And so because the force and the displacement vector are anti-parallel or opposite, based on this equation, work equals force times displacement, the work done on this charge by the electric field is negative. So what does that mean? If the work done is negative, that means that the kinetic energy is decreasing. If you recall from the work energy principle, work is equal to the change in kinetic energy. And when the kinetic energy goes up, the potential energy goes down. And if the kinetic energy goes down, the potential energy is going up. So the change in kinetic energy is equal to the negative change in potential energy. So in this case, this charge is losing kinetic energy. It's slowing down. However, its potential energy is increasing. Now, this situation is analogous to, let's say if we have a ball placed above the ground. At this point, above the ground, it has high potential energy, and the ground has low potential energy. And so as the ball falls from a position of high potential energy to low potential energy, we could say that its potential energy is decreasing. But it's speeding up as it falls to the ground, and so the kinetic energy is increasing. Now, this ball is falling down, so its displacement vector is negative. It's going in the negative y direction. But the gravitational force acting on this ball is also in the negative y direction. So because the force and the displacement vector are in the same direction, the work done on this object is positive. And anytime the kinetic energy is increasing, the work done on that object is positive. So if the change in KE is positive, the work done on that object will be positive. So this situation where the ball is falling towards the ground is analogous to this situation. Let's say if we have a positive plate at the top and a negative plate at the bottom. A positive plate has more potential energy than a negative plate. So this would have high potential energy, and this will have low potential energy. Now, in the case of the ball falling to the ground, at the top, it has high gravitational potential energy. But when dealing with charges, we need to say electric potential energy. Sometimes you'll see me write EPE for that. Now, as the positive charge, let's say if we place it at the top, as we know, it's going to accelerate towards the negatively charged plate. And so it's also moving in that direction, and it feels an electric force pulling it in that direction. And so just like the ball falling towards the ground, we know that the work is positive, that is the work being done on the positive charge and on the ball, and the kinetic energy is increasing because it's speeding up. And as it moves from high potential energy to low potential energy, the potential energy is decreasing. Now, we talked about another scenario where a positive charge was given an initial velocity towards the positively charged plate, but it still feels a force that accelerates it towards the negatively charged plate, because a positive charge will always feel a force in the same direction as the electric field. For negative charges, it's opposite to that. So in this case, we said that because the force and displacement vectors are antiparallel, the work done on this charge is negative. And as it goes up, but the force is trying to bring it down, it's slowing down. So the kinetic energy is decreasing, but the potential energy is increasing because it's moving towards a position of high potential energy. That is a position of high electric potential energy. Now the same is true for the ball in this case. So imagine if you throw a ball upward in this direction. Actually, let me draw it here. So let's say the ball is going up. It has an initial upward velocity. Gravity is still acting on the force to bring it down. Now the ball, because it's moving up, it has an upward displacement vector. So because these two are opposite to each other, the work done on this ball is negative. As the ball moves towards a higher position, it's moving towards higher potential energy. So the potential energy of the ball is increasing. But as it goes up, it's slowing down, and eventually it's going to reverse and go back to the ground. So as it's going up, it's slowing down. Its kinetic energy is decreasing. And you can see the situation is the same here. And so by relating these two concepts, you can tell if a charge is going to, if positive work is being done on a charge, or if negative work is being done on it, and if it's speeding up or slowing down. Now we need to visit something called electric potential. This is the next topic that you need to learn after electric field. So what is meant by the term electric potential? Electric potential, represented by the symbol V, is the ratio between the electric potential energy of a charge and the magnitude of the charge. The unit for electric potential V is the volt, and 1 volt is equal to 1 joule of potential energy, that is electric potential energy, per 1 coulomb of charge. And a good way to understand the concept of electric potential is using those two plates again. Now, it's important to understand that the difference in electric potential is really what can be measured, and so that's the important stuff. Electric potential itself is an arbitrary number. It's only useful if you compare it to the electric potential at another position. So let's say that the electric potential at the negatively charged plate, we're going to say it's 0 volts. And the electric potential at the positively charged plate, let's say it's 100 volts. Actually, let's say it's 5 volts. Now, let's say if we have a positive charge at position A. Well, let me move it close to this plate. So let's say it starts directly on the positively charged plate, which we'll call position A. And it accelerates towards the negatively charged plate. And let's say it's a 1 coulomb charge. So this 1 coulomb charge is moving through a potential difference of 5 volts, from 5 to 0. And we know that it's going to gain kinetic energy during this process, and it's going to lose potential energy. So in this case, now keep in mind 1 volt represents 1 joule per 1 coulomb of charge. So when a 1 coulomb charge moves through a potential difference of 5 volts, 5 joules of work is being done on that charge. Now, whether the work be positive or negative, it depends on the situation. Is it moving from A to B or B to A? Now we know that as it moves from A to B, the kinetic energy is increasing. So therefore, the electric field is doing 5 joules, that is positive 5 joules of work on this 1 coulomb charge. And so we could say that the charge loses 5 joules of potential energy during this process, or we could say that it gains 5 joules of kinetic energy. Now, let's compare it to another charge, but this time we're going to say this charge has 2 coulombs of charge, and it's moving from A to B. In this case, we could say that 10 joules of work will be performed on this 2 coulomb charge as it moves from A to B. And so we can also say that it's losing 10 joules of potential energy or gaining 10 joules of kinetic energy. Now, this leads us to an important equation. So the work done from moving a charge, let's say from B to A, is equal to negative Q times the electric potential difference between points A and B. So you could say it's equal to negative Q times VA minus VB. So let's say we have two charged plates again. But this time we're going to use an electron. And let's say the electron is initially at the positively charged plate. Now naturally it doesn't want to move towards the right. It's repelled by the negatively charged plate. But let's say we use an external force and force it in this direction. So this is not the force generated by the electric field. We're using an external force to move it, let's say from A to B. Now let's say the potential at this plate is 0 and at this plate is 50. Now let's say this is just a negative charge, not necessarily an electron, but there's many electrons. And so let's say the total charge of that object is 20 microcoulombs, but it's going to be negative though. How much work is done by moving a charge from A to B? And is the work positive or negative? So right now, the displacement of the negative charge is towards the right. The electric field is also towards the right. But a negative charge will feel an electric force that will accelerate it in the opposite direction of the electric field. So even though we're using an external force to move it from A to B, the negative charge still feels an electric force that will attract it or pull it towards the positive plate. Now, because the electric force and the displacement vector are anti-parallel, the work done by the electric force is negative. Now let's see if we can quantify this answer. Now we're going from A to B and not B to A, so this equation is going to change. So we're going to say the work done on the charge going from A to B is equal to, and I'm going to focus on this portion of the equation, negative Q times the electric potential difference between point B and point A. So VA is the electric potential at point A. VB is the electric potential at point B. But it's the difference in electric potential that really matters. And you know what? Let's change the charge. Instead of using micro, let's use a nice whole number. Let's say negative 4 coulombs. Now, if you recall, whenever a charge moves through, let's say, a potential difference of 1 volt, a 1 coulomb charge will have 1 joule of work done on it. It could be positive or negative, but it's going to be 1 joule of work. In this case, we have a 4 microcoulomb charge moving through a potential difference, so let me write delta V, of 50 volts. And so in this case, it should be about 200, because a potential difference of 50 volts means that the charge can gain or lose 50 joules of energy per 1 coulomb of charge. So it can gain 200 joules of energy or lose 200 joules of energy per 4 coulombs of charge. So using this formula, we have negative Q. Now Q is negative 4 coulombs because we're dealing with a negatively charged particle or object. And VB, the potential at point B is it's 0. The potential at point A is 50. So we have two negative signs. A negative times a negative is a positive. And 0 minus 50 is negative 50. So overall, this is going to be negative. So it's negative 200 joules of work being done on this negative charge. And so just as we predicted, the work was going to be negative when the negative charge moves from position A to B. So hopefully this section gave you a good understanding of the concept of electric potential energy and electric potential. So make sure you understand the difference. V represents electric potential without the word energy in it, just potential. And the unit for electric potential is the volt. So when you think of a 9-volt battery, what this tells you is that it can do 9 joules of work when it passes 1 coulomb of charge through a circuit. And so it helps you to understand the concept of voltage. Voltage is really the difference in electric potential. It's the change in the electric potential. So it's like VA minus VB or VB minus VA. So electric potential is simply an arbitrary number. It's simply V. But delta V, that is a voltage, which is more commonly used in everyday applications. So make sure you understand the difference between electric potential and voltage, and also electric potential energy, which is PE. So remember, 1 volt or electric potential is the ratio between electric potential energy and charge. And the work done by a charge or on a charge is negative Q delta V. And that is as the charge moves through an electric field or through an electric potential difference.